Hey Algebra 2 classes, my name is Miss Marsh. Some of you in Temecula may know me. Hello to the people in Temecula and also in Hemet. So we're going to be going over the assignment that is day 2A for Opt 2. And this is, I believe, page 273 in your book. So, topic of this lesson is satisfactory factoring polynomials to identify some zeros. Some prerequisite things that you need to be able to do that you may want to review beforehand is factoring trinomials, the quadratic formula shows up a little bit in this, and complex or imaginary numbers. But I'll review them a little bit as we go through this lesson, okay? All right, so the learning goals is we want to factor higher order polynomials. You may have done factoring in the first opt, but those were second degree. Those were quadratic. So now we're looking at third degree, fourth degree, so higher exponents. We want to distinguish between factoring polynomial equations over a set of real numbers or a set of complex numbers. So when you think of complex, you should think imaginary and real put together, okay? Complex means imaginary number sets plus real number set. So we're including imaginary numbers. So things like I, which is the square root of a -1. We're also going to identify zeros of polynomials when suitable factorizations are available. Okay, so just reviewing that word right there, a zero is a value that makes the polynomial equal to 0. Which, when you're talking about a polynomial function, that relates to the x-intercepts. And so if you know the zeros of a polynomial, you know the zeros, or you know the x-intercepts of the function, and then you could then use the zeros of a polynomial to sketch a graph of the function. Okay. So let's get into it. So the first page, we have some review questions, and that is solving equations such as these, okay? First two questions look like this. We've got 2x squared minus 4 is equal to 8, and x minus 1 cubed minus 5 is equal to 0. And then we have two more that I have on the next page, 3 and 4. So to solve these types of equations, we need to first isolate the power, okay? Then undo the power. So if it's a square, we can take a square root. If it's a cube, we could do a cube root, or a fourth if a fourth root. And there's actually a third step, and that is just solve remaining equation using inverse operations. Okay, so let's pause the video and have you guys try number 1, number 2, number 3, and number 4 using these steps. Okay, so let's go ahead and show you how to do these. For number 1, we have 2x squared minus 4 is equal to 8. So the first step was to isolate the power, which is the x squared. So isolating a power means to undo what's happening to it. We want to, just like in any equation, you're doing inverse operations. So I see we're multiplying by 2 and we're subtracting 4. You do want to undo them in the reverse order. So we're going to start by adding 4 to both sides. Which gives us 2x squared is equal to 12. Now be careful here. The only thing that is being squared is the x, not the 2. The 2 is a coefficient. Okay, we have to get rid of it, so we're going to divide both sides by 2. And that leaves us with x squared is equal to 6. So that is isolating the power. The x squared is now isolated on one side of the equation. We're then going to undo that power by taking the square root, cube root, fourth root, in this case a square root. And when you take an even root, like a square root, you need to take the plus or minus square root. So I'm going to take the plus or minus square root of both sides. And that is going to leave me with just an x on the left side. And then on the right, we're going to have plus or minus the square root of 6. There's nothing else to do here, so step 3 was kind of optional. So I will write this as optional. It kind of, well, not optional. It may or may not be necessary is what I'm trying to say. Okay, so if necessary. Okay, and it didn't specify that we wanted to round any decimals, so we're just going to leave it in simplified form and we're done. Okay, we got plus or minus the square root of 6. Can't simplify the square root of 6. All right, let's take a look at number 2. Now the power here is a little bit more complicated. It is this whole thing, x minus 1 in parentheses to the third power. That is what we need to isolate. So that means we only have to do one thing, and that is add 5 to both sides. I mean, to isolate the power. There's more to be done after it, but. So we're left with x minus 1 cubed is equal to 5. Okay, now we can undo the power. This is a cube root. When you're doing an odd root, you do not have to worry about the plus or minus. So we can just go ahead and take the cube root of both sides. We don't have to worry about the plus or minus. The cube and the cube root will cancel, leaving us with just what's underneath, or what's inside the parentheses, which is x minus 1 is equal to the cube root of 5. We're just going to leave it as the cube root of 5. We're not going to mess with decimals right now. Then what we can do is we can, now we have this extra step we have to do. We have to solve the remaining equation for x by using inverse operations. So x is not alone. We got to get rid of this minus 1. And so let's add 1 to both sides. Okay, now when you add 1 here, it cancels. But when you add 1 to the right, it doesn't become like the cube root of 6. A cube root of 5 and a 1 are completely different terms. So what you're going to want to do is you're going to want to just tuck it in front of the radical, and we're going to do 1. And since this is a positive number, we're going to add the cube root of 5. You could also write it as the cube root of 5 plus 1, but it is standard to not put anything after the radical if you can avoid it, because it could start to look like this. And because that radical sign could get extended and our handwriting can be messy, and then that's a completely different thing mathematically, so we don't want to do that. Okay, let's take a look at the last two. Again, isolate the power, undo what's happening, undo the root, and then get x alone. Okay, so I'm going to isolate my power. So just like in the last one, my power is inside the parentheses, or it's including everything in the parentheses here. So this is my power. So I need to get rid of the times 3 and the adding 11. But we need to do it in the correct order. If you're not sure what order to do it in, just think of like 2y plus 11 is equal to 15. How would you solve that? We'll say 3y, so it looks like this one. All I did was I replaced this with y. I know every Algebra 2 student can solve this. It's a two-step equation that you learned in like 8th grade, or you want to subtract the 11, right? And then you want to divide by the 3. Okay, that should seem pretty familiar. What we're working with is pretty much the same thing, just a little bit scarier, but just the first part is just doing exactly the same. Subtract the 11, and then we're going to divide the 3. Okay, but what we're left with is not x equals or y equals, it is x minus 6 to the 4th power equals 4/3. Okay, so that gives us our first step. We isolated the power. Now we have to undo the power. So we are going to take a 4th root. So remember, an even root, you want to use plus or minus. If it's an odd root, you don't. And that goes back to the idea, if you take something that was negative to an even power, the negative will always cancel and it'll become a positive. Like when you square a negative, it becomes positive. So when we're undoing a square, we need to include that negative as a possible answer. Okay, so I'm going to take the plus or minus 4th root. Plus or minus 4th root. Okay, that gives me, now this is gone. Don't worry about the plus or minus on the left side. It's mostly about the right side. And we have x minus 6 is equal to plus or minus the 4th root of 4/3. Be careful about how you write that 4. If you write the 4 too big, it will look like a 4 times the square root of 4/3, which is not what we mean. Okay. So then what we need to do is add 6 to both sides. And just like before, I'm going to tuck it in front. So our final answer here was x equals 6 plus or minus the 4th root of 4/3. Okay, last question. It's actually the simplest one. Isolate the radical, or the power, I mean. We just got to get x cubed. So we should add 27. And then from there, we need to take the cube root. We don't need a plus or minus. And this one actually has an integer answer. Do you know what it is? If you said 3, you're correct. The cube root of 27 is 3 because 3 to the 3rd power is 27. Okay, there's our review. So now we're on to the getting started. Make sure you're following along in your book. Okay, so here's our getting started setup. We have factor tree factory. At the factor tree factory, a factor machine takes any whole number as input and outputs one of its factor pairs. Okay, so suppose you enter the number 24 into the machine. What factor pairs might you see as the output? So we're thinking of pairs of numbers that are going to multiply to make 24. So I want you to list all the pairs of numbers that you know that multiply to make 24? Okay, let's see if you came up with all of them, because there's quite a few. Now there's 1, 2, 3, 4. So you may have come up with 2 and 12. We've got 3 and 8. 4 and 6. And there's one more. Everybody forgets this one. 24 and 1. So how do you know that whether two numbers are a factor pair of 24? Well, I kind of gave it away. They need to have a product, or they need to multiply to equal 24. Okay? So they must multiply to equal 24. Something along those lines. Can 5 be an output value? What do you think? Is it possible? So when we're talking about factors, we're talking about numbers that go into a number evenly, so to speak, which means they do not have a remainder. If you were to try and divide 24 by 5, you would get a remainder. So there's no other integer, whole number, that would multiply by 5 to get 24. It would have to be a decimal. Okay? So I'll leave you to kind of answer that in your own words. So let's talk about factor trees. So in question 2, Charisse and Gemma each begin a factor tree for 24 using different outputs from the factor machine. So we can see Charisse is using 2 times 12. There we go. And Gemma is using 3 and 8. He says both factor trees will show the same prime factorization when completed. Gemma says because they each started with a different factor pair, the prime factorizations will be different. Who is correct? So I want you to pause and think about this. Well, let's discuss it. So these factor trees are not done. If we keep completing them, we're going to break down the numbers further, and we can get the prime factorization. So a prime factorization is breaking down a number into its prime factors. So if that word is a little familiar but you don't remember what primes are numbers that can only the only factors of prime numbers are itself and 1. So examples of prime numbers are 2. 2 times 1 is the only thing that multiplies to make 2. 3, not 4, because 4 is 2 times 2. 5 is. 6 is not prime. 7 is. 8 is not prime. And if you're thinking, oh, it must be 9, nope, 9 is not prime. So there's a lot of odd numbers. In fact, 2 is the only even prime, because all other even numbers are divisible by 2. So all the other numbers are odd, but not all odd numbers are prime, like 9 is not. The next odd number, or the next prime number, is 11, and it goes on and on. Okay, so let's complete each factor tree to see how it goes. So let's do Charisse. 2 prime. I'm going to circle it because I can't do anything else with that. 12 is not prime. 12 is 2 times 6. 2 is prime, so I'm going to circle it. 6 can be broken down into 2 and 3. So the prime factorization of 24 from this tree is 2 times 2 times 2 times 3. Those are the primes. I'm just basically copying the primes here. 2, 2, 2, 3. 2, 2, 2, 3. So let's look at Gemma. 3 is prime. I'm going to circle it. 8 is 2 times 4. 2 is prime. And 4 is 2 and 2. Notice we get the same primes. We have a 3, a 2, a 2, and a 2. They're identical. Doesn't matter how you set up the factor tree, you're going to get the same primes in the end. So who was correct? Charisse was correct. Go ahead and write your own explanation as to why, okay? Justify your answer. So consider the expression 2, 2, 2, 3. How does 2, 2, 2, 3 relate to the factors determined by Charisse and Gemma? We just saw that those were the prime factors. Okay, they are the prime factors of 24, or the prime factorization. And I guess I should change my grammar. It is the prime factorization of 24. And how does it relate to 24 other than it being the prime factorization of it? You can say it's the product, or 24 is the product of all these numbers. If you multiply 2 times 2 times 2 times 3, the product is 24. We can try it. 2 times 2 is 4. Times another 4 times 2 is 8, and then 8 times 3 is 24. Okay, you know a given factor of a given whole number, or when you know a factor of a given whole number, how can you determine another factor? Okay, let's do an example. Let's say you know that 7 is a factor of 56. How can you determine another factor? What do you think? Did you think about dividing it? Because that's pretty much what you would do. You can divide the factor into the number. Okay, or if I know a factor, divide it into the number to find another factor. For example, 7 is a factor of 56. So you can do 7 into 56 is 8. That gives you another factor. Then from there, you can even make a full factor tree. You can break down the 8. 2 is a factor. 4. 14 is a factor because you can kind of move the 2 times the 7. Okay, so what is the remainder when you divide a whole number by any of its factors? I think we know this. The remainder is 0. We mentioned that earlier. Okay, when you divide a number by a factor, it should go in evenly, so there shouldn't be a remainder. So why are they talking about all this? What does this have to do with anything? Well, this topic is really going to get into polynomials and all of their factors. And how do we know when something is a factor of a polynomial? Well, you need to get a remainder of 0. Well, that means we have to learn how to divide polynomials, which is coming up, okay? It's all kind of getting into, we're going to take all this stuff about numbers and apply it to polynomials. Okay, go ahead and make a couple factor trees. I think you guys can do that. Go ahead and pause it, make the factor trees. And when you're ready, unpause it. All right, check your work. So you could start the factor tree any way you want. Instead of 66, you could have done 33 times 2 or 22 times 3. I did 6 and 11, and then 6 is 2 and 3. So the factorization is 2 times 3 times 11. And then 210, I did 21 times 10. But again, you can start with two different things. And then the prime factorization, you get a 2, a 3, a 5, and a 7. All right, so now let's talk polynomials. So we're going to split this up into two videos. So that was the first video, and we'll do activity 1 and activity 2 in the second video.